Alright, so in this video we're going to talk about projectile motion. Particularly, we'll be describing the motion of a body thrown at an angle with an initial velocity of v under the influence of a constant force of gravity, which is something that we feel on the Earth. Alright, so we're going to talk about different parameters that describe a projectile motion, or basically motion in two dimensions. The three quantities that we will deal with are maximum height, range, and the time of flight. So a quick description of what we will actually be doing is the following. So if you have, say, the green Earth, and you're throwing a ball from the Earth at a particular angle, and you're giving it an initial velocity of u vector and a theta of, well, and an angle of theta, then you see that the ball actually takes the form, the motion of the ball takes the form of a parabola, which is like so. We can also prove this, but for the purpose of this video, let's assume that this indeed is a parabola, and then the ball takes this kind of form. All right. So there are many parameters associated with this form of motion. We call this motion projectile motion, and the parameters associated with this are, well, the maximum height, which we can denote by h sub max. That's the maximum height that the ball attains at the point where it only has a horizontal component of velocity. The other parameter is, well, the range, and that is given by r, and that measures the horizontal distance, the farthest horizontal distance the ball assumes while it's in motion. Now, there's another parameter which is associated, which is called the time of flight, and time of flight basically is the total time duration for which the ball was in the air, continuing its projectile motion. So that is the time the ball takes from starting at this position, going all the way here through the maximum height position, going and falling back at the maximum r position or the range, and this point right there. So the total time period for which the ball was in the air is called the time of flight. All right. So with that description, we will understand what happens to a very general case of a ball which is thrown in this manner, and we'll try to figure out what the values of maximum height, range, and the time of flight are with respect to the initial parameters of u and theta. All right, so let's begin. So imagine, if you would, you have the Earth, the flat Earth, and you're throwing a ball from the Earth, right, and you're giving it an initial velocity of, well, u, and we denote it by u vector because now it has a direction, and say the angle at which you're throwing it is this angle, and we call that theta. Now we let the ball proceed with this initial velocity, and we see that due to the force of gravity, which is acting downwards at all times, the ball assumes a motion, a trajectory like so. So that's the best dotted line I can manage, and this is what we call a projectile motion. All right. So there are 3 points where we will actually be describing what's happening to the ball. First point is the initial point. All right. So at the initial point, what is the velocity? Well, the initial velocity is u, and this is something that we already know. What is the angle at which that's oriented? Well, it's oriented at an angle of theta. So we also know that. So we know quite a bit about the dynamics of the ball at the initial point. All right. So that's kind of dealt with. Second of all, the second point is the point at which the ball attains the highest height. So that is the point right in the middle of this trajectory. And for reasons of symmetry, we can assume that that's right in the middle. And at that point, what really happens is the ball is at its highest position. Now, if something is at its highest position, that means it has no capacity to go at a higher position than that. So the only way in which this ball cannot go higher than this point here is if its vertical velocity is 0. So at this point, we can safely assume that the ball is going to have only a horizontal component of velocity, which will be, well, some velocity. We have to figure that out, but we certainly know for a fact that there would be no vertical component at this point, and this is some velocity. All right. And the last position, which is this position right there, because of the symmetry argument that we are, which is basically undertoning this entire video, is the fact that this point will basically be symmetric to this point. And at this point, the ball is going to fall back to the ground with a mirror velocity of u. So that is to say that if it were having a velocity right before impact, that velocity vector would be oriented at theta angle in the negative now, and would be having the velocity of well, the magnitude of u vector, the initial velocity that we started with, but the directions would be symmetric, as you can see already. So these are the 3 points at which you may see questions in your respective examinations, and so on and so forth. So 3 points are very important, all right? Now, let's write out what we're actually figuring out in this video. Well, the first thing that we will encounter is the h max, which is the maximum height. Second thing would be the range, and the last thing would be the time of flight. All right, so h max is this height. Let me write that out like so. And the range, or r, is this entire distance, the distance in the horizontal, like so. And the time of flight is the time during which the ball was in the air. All right, so let's figure out what's happening to the ball. Now, the ball is being thrown at an angle of theta, right? That means it will have two components of velocities at all times. One would be a horizontal component, like so. So this would be the horizontal component, and you will have an initial vertical component like so. All right, so for a better diagram, let's think about that here. If this is your u magnitude, and this is your triangle, then we clearly know that the two components would be, well, this, the horizontal, and the vertical component would be vertical, like so. All right, now we also know that this angle is theta. That means the length of this would be the length, the magnitude of horizontal velocity, which would be u cosine theta. And this here would be, well, u sine of theta. Now these are just rules of trigonometry. You can think about this as SOHCAHTOA rule, or the sine cosine rule, or whatever way in which you remember cosines and sines. And that is something that we're employing here in order to figure out the other sides of the right angle triangle, given the hypotenuse on one of the angles. All right, so that is clear to us. That means the ball is going to have an initial velocity of u sine of theta in the vertical, so let me write that down here, and u cosine of theta in the horizontal. All right, now remember the gravity is only acting in the vertical direction, so it's only going to impact this component of velocity. So this will be only impacted by gravity. This is the only component of velocity which will be impacted by gravity. What that leaves is this component of velocity, which is untouched by gravity. And that is interesting because if you think about this entire motion, what's really happening is that the vertical component of velocity is changing at every point. At this point, the vertical velocity will be something lower than this. And at this point, the vertical velocity is absolutely zero. At this point, the vertical velocity component is in fact negative, and at this point, it's back to this this length, which is the same length as u cosine theta, but in the negative. All right, so the vertical components are changing, but what's not changing is the horizontal component. So if this is u cosine theta, then I'll do my best to make the same length of well, the horizontal component of the velocity at this point, and this would be u cosine theta again. And so what this leaves us is this vector here. Well, since this vector is the untouched horizontal component, it should be the same as u cosine theta at this point. So at the highest point, we know that the velocity of the ball is u cosine theta. And at this point as well, it will be u cosine theta, and so would this be at this point. So you see the horizontal components are untouched, but the vertical components are very much affected by gravity. All right. So the many ways to think about projectile motion, and the most convenient way goes as follows. Since there are two components of velocities, one of which is untouched, the other one is actually being impacted by gravity, we split the motion in two directions. So the first direction of motion is basically this vertical motion. So that's as though the ball was right at this point and we did not give it any horizontal velocity. So the ball fell on its own position and really had no horizontal component of direction. The other component of velocity was u cosine theta, which was just a simple non-accelerated motion, which continued for this length till the time of flight. All right. So with this vertical component of motion, this is what's happening to the ball. And the other way to think about this is, say, if you had a light source here, something like that, and you look at a wall here, then the shadow of this ball, as what you will see at all points, would be basically this vertical motion. All right. So that's what's happening here. Now, what is the vertical component of velocity? Well, initially we know that at time equal 0, the initial component of velocity was, well, u sine of theta. So that's the velocity initially. At the highest point, well, the velocity was 0, all right, because that's the case at this point. And at the lowest point again, when it went back, the velocity again would have been, well, minus u sine of theta, right? And that's with a sine. So if this is our displacement vector, like so, going from this point to the maximum point, then using the three laws of, well, the equations of motion that we already know, so all of them are v equals u plus at, s equals ut plus half a t square, and the last one is v square equals u square plus 2, the dot product of a and s. All right, so we can use these three equations in order to figure out h max. All right, so let's try to do that, and we see very clearly that if we are to figure out this s vector, this s vector is nothing but h max vector, which is right there, because at this highest point the ball is at highest height. Remember that. So that means if this is our s is known, and we know the initial velocity, we also know the final velocity, we know v and u, then there's only one equation we can use to evaluate what s would be. That's very easy, because the other thing that we need to know for this is the fact that gravity is acting in the minus direction. So let's try to use this equation and see what we get. All right, so at the point where v is 0, u is u sine of theta, a is minus of g, and s is h max, then if we use this equation, we get, well, 0 square equals u square sine of theta square plus 2 times g with the minus sign times h sub max. And you can solve this and you get h max equals, well, u square sine square theta divided by 2g. So that's what the maximum height that the ball will attain would be. So we have it here, and we are writing it as follows. So the maximum height that the ball would attain would be like so, it would be u square sine square theta divided by 2g. And so we have figured out the maximum height given u and theta. We already know g, so that's something that's already assumed. All right. Now let's talk about the time for which it is taking to execute this motion. All right. So the time for the horizontal motion will be the same as the time for the vertical motion, because ultimately at this point the horizontal and the vertical motion are completed at the same point. So if we are to figure out the time for which the ball starts at t equals 0, and this is some time here, right, and then it goes back to ground, to the ground level again, then this entire time duration would be, well, capital T. So that's the time of flight for which the ball is in the air. So the highest point, because it's a symmetrical motion, the time at which the ball is at the highest position would be the time of flight divided by 2. Half of this, t by 2 is the time that it takes to fall down, and t by 2 is also the time it takes to rise up. So there you have it, that's the time at the highest position. Now remember, we know h max, which is u square sine square theta by 2g. We know t, which is a variable, we have to figure that out. We know initial velocity, which is u sine of theta, and we know final velocity, which is 0 for the first half of the motion. Now we ask ourselves, what is t, right? So the simple way to go about that is to use this equation right here. So if we use this equation and we substitute v as 0, u as u sine of theta, well, substituting it like so, a as minus of g, and t as, well, the time for the first half of the flight, which is t by 2. If you substitute all that, you get 0 equals u sine of theta plus minus of g times capital T by 2. So you solve this and you get t equals, well, 2u sine of theta divided by g. So there you have it. Wonderful. That's the time of flight for the motion of the projectile. So that's interesting. So we also have this component here, which is 2u sine of theta divided by g. That's interesting. That's really nice. Now, you may be thinking, why haven't we employed the second equation? Well, you could employ the second equation because now you know s, you know u, you know A in order to figure out what t would be. Now remember, t would again be substituted as capital T by 2. However, this is a bit difficult to solve. Why? Because you see, you will have a quadratic equation in the variable for small t. And that means you will get two answers, and you will have to either ignore one of them because time would be negative in that case, or you would have, or both the roots would be the same. You know, you have those kind of criteria for solving this second equation, right? So that would make our lives a bit more tedious. So we chose this easy way out, which was the first equation and the last equation, and they helped us evaluate the time of flight and the maximum height that the ball attains. All right. Now we are left with one last question, and that the last question is, well, what really is r, or the range of flight? All right. So the range of flight would be, well, we know that, oh, well, forget the vector for now. The range would be the total time, basically the horizontal component of motion that it acquires in the time 2u sine theta by g. So we know the total time for which the ball is in the air. We also know the initial component of velocity. We know time, we know velocity. Basically we need to use, well, v equals d by t in order to figure out what d would be, or speed equals distance upon time. You know, so this is the same as speed. The other way to think about this is, since we know one of the equations is v equals u plus a t, and we use it in the horizontal direction, remember, this in the horizontal direction becomes, well, a in the horizontal direction is 0, so you get v equals u. That means, finally, at this point as well, the horizontal component would be u cosine theta, all right? So you can evaluate that, and you can also use the second equation, which is s equals ut plus half at squared, all right? And what is a again in the horizontal direction? Well, a is 0 again, so you get s equals ut, which is the same as u equals s by t, and that's the same thing I've written here, all right? Which is displacement upon time, and displacement was capital S. So the same thing. So the range would be this capital D, and that would be equal to the velocity that you have multiplied by the time during which the ball is in the air. All right, so the range would be the velocity, horizontal component velocity, which would be u cosine theta, multiplied by the time of flight, which is capital T. All right, so we can also expand t because we know t in terms of the initial parameters of the motion, which is u and theta, and we write that as follows: u cosine theta multiplied by 2u sine of theta by g. All right, and the last thing to do is to combine this. We get 2 sine of theta cosine of theta multiplied by u divided by g. All right, so that's interesting. What's really fascinating is now what we can do is we can employ trigonometric identity, which basically expands sine of 2 theta, and we say sine of 2 theta is equal to 2 sine of theta into cosine of theta. And because that's true, and you can check this in your mathematics books, you get this factor as sine of 2 theta multiplied by u by g. All right, so we have figured out what the range would be, and that is sine of 2 theta multiplied by u divided by g. So there you have it. That's everything you need to know about a projectile motion in the field of gravity or in the force of gravity. All right, so I hope you like this video, and I hope it made sense to you. If you have any questions, put them out in the comments. I'll be very happy to answer them, and all the best.